Okay, Assalamu alaikum, dear students. Let's start from where we left. We last time proved some consequences of the Han-Banach theorem. There might be a couple more which you can do yourself, which you can do it from your notes. But let's now turn to some other topic and we look at duals of some concrete normal linear spaces. Now we know that what's a dual. Now if X is just to repeat normal linear space, then X star is basically all functions from X to the scalar field K such that F is linear and modulus of Fx is, which means it is continuous, some K times norm of X for all X belonging to X. Now you know that. Now we take some concrete examples of normal linear spaces or Banach spaces that we already know, like L1, like LP. Now the summable sequences, the pth power summable sequences, like many others, like CAB, and look at realizing the duals as some, because this is also a normal linear space. In fact, a dual is always a Banach space. Now we want to realize X star as a concrete space, not in terms of functions, but as a concrete normal linear space, a Banach space which we already know. For certain examples of X, we want to find certain X stars. Now what we are going to basically do is going to show that they are, if we take suppose L1, we will show that L1 star is L infinity. By that we mean that if I take L1 in place of X here and take all the functions and take all the normal linear space of all bounded linear scalar valued bounded linear functions, then it would be isometrically isomorphic to L infinity. Because if it is isometrically isomorphic to L infinity as a Banach space, it is the same as L infinity. Okay, now this is the background how we are going to do it. Not background, this is going to be our method of identifying the duals of certain concrete normal linear spaces. Now the idea would be basically, let me motivate our method, our technique of doing what we are going to do by an example. Suppose I take R3 as my X. That means all triplets, all vectors in three-dimensional space, right? Now it is a normal linear space, and let me take it to be the Euclidean norm. By that I mean norm of every X is of this form: xi square I runs from 1 to 3 whole raised power 1 by 2, or in other words summation x1 square plus square root of this thing, right? Our usual Euclidean notion of length of a vector. Okay, now look at this. Now if I what I do is, if I think of the inner product, the dot product in R3. Now take a specific vector A, a fixed vector A1, A2, A3 belonging to R3, and take it as dot product with, take the dot product of this vector A with any vector X. Now this would be A1 X1 plus A2 X2 plus A3 X3, right? I can think of it, because this is fixed, that this depends upon X, I can think of it as f of X. Furthermore, the expression is these are two, this is a number, this is a number, multiplying numbers and adding numbers, you will get a number. So this belongs to R. In this case, then this map f of X to be the dot product to A of X, I don't put arrows, you understand, they are triplets of numbers, is a map from X to R. And it's very easy to check that it is linear. And if I take norm of f of X, that would be, what would be that? A x1 plus b x2 plus b c x3. Of course it would be if you use what we call, you have done that in your earlier semester, the Cauchy-Schwarz inequality. This would be less than equal to root of a square plus b square plus c square into root of x1 square plus x2 square plus x3 square. Now this is going to be, if I think of it as a number, because this is of course a number, this is square root of the squares, sum of the squares of three numbers, therefore a number, a positive number. So then this would be less than equal to k times norm of x, because my norm is defined by this. So it is indeed a bounded linear map. So what the idea is that this single vector belonging to R3 gives rise to a functional defined on R3, right? Because it is now this is actually x is R3, so f is a map from R3 to R, so it is linear and continuous, so f belongs to R3 star, but f was generated by a vector belonging to R3. So a vector can be associated in this way with a functional on a certain space. So, and actually converse is also true in this case. Every functional would be of this type. For every functional there would exist a specific vector like this which would generate it exactly in this way. Okay, now what we do is we move ahead. Now this was a simple case. Now we start with duals of concrete spaces, keeping this in mind. Now what I already have now this example, this motivating example in mind. Now before that, we just want to do away with a definition that's called a Schauder basis. Now you already know what is a Himmel basis, or every vector space has a Himmel basis or a vector basis. Himmel basis, vector basis, or simply a basis of a vector space, right? So if you have a vector space X, right? So if you can find as B a subset of X such that, for of course X is a vector space over some field K, right? This is a vector space over some field K. If you can find a subset of vectors in X such that for every X belonging to X, there exists a unique finite set of scalars alpha I belonging to K such that X is equal to summation alpha I xi finite, where xi are contained inside B, right? So remember that this finite is important, right? So this set of vectors B is called a vector basis or a Himmel basis or simply a basis of this vector space. Now Schauder basis is defined for normal linear spaces. So it is again a basis. Of course there are similarities between the two, but there are also essential differences, because every normal linear space has a vector basis, so it may or may not have a Schauder basis. Okay, so it is defined basically only when you have a norm defined on a vector space and you have a normal linear space. This is defined whether the norm is defined or not. Every vector space would have a Himmel basis. Okay, now Schauder basis is defined as, if you have an X as a normal linear space, of course the proper definition is in your notes, then a set, of course it's a subset, let me call it xi, a finite, infinite, whatever, is contained, which is contained in, of course, X, is said to be a Schauder basis. Said to be a Schauder basis for X if for every X belonging to X, as you can see the similarities between the definition, there exists a unique set of scalars alpha I which is contained in K, finite, infinite, whatever, such that norm of X minus summation alpha I xi, I runs from 1 to n, goes to 0 as n approaches infinity. And if that is the case, then we take the liberty of writing x as summation I runs from 1 to infinity alpha I xi. Now again, of course, this is only possible because the definition involves the norm itself. So this is defined for normal linear spaces. Now it's obvious, again, you can do an exercise that if you have L1, that is summable sequences, and if I take my vectors, I can take EI, it's a Schauder basis. The sequence of vectors is a Schauder basis for L1, in fact also for L infinity and LPs, of course. You can check. I would encourage you to do it on your own. So where EI is defined to be 0, 0, all zeros, and 1 is only at the ith place. Rest of them are 0. It's a sequence. Of course, this is a sequence in L1, L infinity, P to the power summable. These are always there. And furthermore, they act as a very, well, in a straightforward way, that it acts as a Schauder basis on these normal linear spaces. Okay, now let's come to our duals. So we take some concrete example of a normal linear space, a Banach space, and show that it has a dual. Now first one, the simplest one, not simplest, but this is what is going to set the things right. We start with this, that L1 star, the dual of L1 is L infinity. That means basically L1 star is isometrically isomorphic to L infinity. So let's start with the proof, and you will see that what I said about that example would play out in this method, in this proof, the method of our proof. So let f belong to L1 star. So it's a bounded linear map. Now remember that f now is a bounded linear map defined on L1, taking its values in the scalar field, which is linear and continuous, right? Now, okay, now we know that, as I told you to do it on your own, that ek, let me call it k, where ek is equal to 0, 0, 0, 1, 0, so on and so forth, a sequence which has 1 at the kth place, everything else is 0. Now this of course belongs to L1, and furthermore it is a Schauder basis for L1. Okay, so if x belongs to L1, I can find scalars. So there exist unique scalars. Let me call them xi or xj, xk, whatever you use the index, contained in k, such that x can be written as summation xk ek. No, I had this alpha I ei. Now in place of alpha I have got xk. So let's call it k, so that you don't get confused. But you shouldn't get confused by just the change of alphabet, as long as formulas are the same. So now x belongs here, so f belongs to L1 star. F would act on this x and give us a scalar, right? So fx is a definite number, but then fx is also equal to summation k runs from 1 to infinity xk ek, right? So this is a number, but this number, because f is linear, this means that I can write it as summation k runs from 1 to infinity xk f of ek, provided this now is a series of numbers, provided this series converges. If this series makes sense, right? It has to make sense, because f of x makes sense, because left hand side is what? Left hand side is a defined number, because f is by default a map. So it would send a vector in L1 to some number. So this is a well-defined number, although it's an infinite sum. right? And since f is continuous, we can, because of continuity, we can take this infinite sum out. Because of linearity, we can do it up to a finite level, but because since f is continuous, we can take the limit outside. Because what is this? Is in fact the limit of the nth partial sums, right? So you take the partial sum out because f is linear, then you take the limit out because f is continuous. So let us write it as summation k runs from 1 to infinity xk yk, where yk is equal to, of course, f of ek. I just substituted, right? Okay. Now yk, and if I take the modulus, is equal to f of ek. Now remember that this this f is a bounded linear map, so this should be less than or equal to norm of f into norm of ek. Why ek1, right? Because ek is a Schauder basis in L1, so by this we know this is how we define, how we denote the norm in L1, small L1, which is equal to norm of f, because this is 1, right? So this means that this sequence, this yks, f of ek's, now this is true for all k. That means this sequence, if I take the sequence now, I mean the sequence y1, y2, so on and so forth, this sequence, that is f of ek's, that I get when I substitute for k 1, 2, 3, 4, of course, is a bounded sequence because it is less than or equal to some number for all k. So it means that this sequence must belong to L infinity, right? And if I call this vector y, this sequence is a vector in L infinity, and furthermore supremum, because all of them are less than or equal to norm f, it means that supremum yk, k greater than or equal to 1, is also less than or equal to norm of f. But this is precisely the norm in L infinity. And I should have first thing is that these scalars, the sequence generated by these scalars, belongs to L infinity, and its norm is less than or equal to norm of f. Let me call it star, right? So what I have got now is that for everything f, for an arbitrary f belonging to L1 star, I have found a vector y belonging to L infinity such that norm of that vector y is less than or equal to norm of f. Okay, now keep that in mind. So something, and if you look at this expression here, and this should remind you of inner product that I showed in the example. Okay, now we show the converse is also true. So what do I have now? So far what I have, for every f belonging to L1 star, I can summarize what I have done thus far. There exists a unique y f belonging to L infinity such that norm of y, of course infinity, is less than or equal to norm of f, right? This is what we have shown. On the other hand, if I take y equal to some arbitrary, let me call it beta kk runs from infinity belonging to L infinity, I'm doing the other way around. So, and I define to be fy sub of x, I define a map by this, let me write it as xk yk, k runs from 1 to infinity, this infinite sum of scalars, right? Okay, sorry, I have taken y to speed. Let me write it as summation k runs from 1 to infinity beta k xk. Let me write it like this. So this map, now this is where x equal to xk belongs to L sub infinity. So this way x belongs to L infinity. Now fyx, now this is a series, isn't it? This is a series, but this is the series where it is the, what is this? This is the product of the individual scalars, the terms of the sequence, and then we sum it up, right? The information we have that these x k's belong to L infinity. Oh, sorry. This belongs to L1. Okay, so the information I have, this x belongs to L1 by our construction, and this y beta k's belong to L infinity, means that this is a bounded sequence and this is a summable sequence, right? So what does bounded sequence mean? It means that these bk's are bounded. All of bk's are less than equal to some number. That means if I take modulus of f of yx, this would be modulus of summation k runs from 1 to infinity beta k x k. Now this would be less than equal to supremum or k greater than equal to 1 beta k into summation modulus xk. K runs from 1 to infinity, and this is nothing but, this is equal to, this is the sup norm, the definition of the sup norm. So this is y sub infinity and norm x1. And since y indeed belongs to infinity and x indeed belongs to L1, these are finite numbers, so this is a finite number. So this series is indeed a finite number. So therefore this is a well-defined map. Fy is a well-defined map from acting upon x, which belongs to L1, and this is a number, so this is a map from L1 to k. So it is in your notes to, it's very easy to show that it is linear. And of course this means that also we have f of y of x in mod is less than equal to something, that is norm y infinity times norm of x1. So that means it is a bounded linear map. So f sub y belongs to L1 star. And not only that, norm of fy, as we have done in earlier things, it must be less than equal to norm y infinity. And if you combined it with our star equation, if I call it double star and combine star and double star, star was this equation. So what do I have? I've got that norm of fy. I can, okay. Now the only thing, so what is fy? Fy is a functional that is generated by a vector y, right? And y is a vector that is generated by f. No, let me correct it. So fy, here I start with a functional f in the earlier part and I get a vector. Here I start with a vector in L infinity and I get a functional f. So there is no harm in calling it fy, because this f gives rise to this y, just to make its association with this y clear, that it is indeed this y is generated by this functional f, so I call it f sub y. So if I combine the two, what I have so far, there is a one-to-one correspondence, there is a bijection, a natural bijection between the vectors in L infinity and functionals in L1 star, such that if I look at these two, because this is less than equal to this and this is less than equal to this, that is what I am trying. When you go through your notes, that means I have got f sub y is equal to norm of y. So where fy belongs to L1 star and y belongs to L infinity. And if there is a bijection, there is a one-to-one correspondence between the vectors in L infinity and functionals in L1 star, such that their norms are preserved, right? So I hope it's coming in the camera properly. Okay, so now what we do, so I define a map from L infinity to L1 star, obviously enough. So I just define f of y to be f sub y. I know that this is a bijection, right? And furthermore, this f is linear. You can do it yourself in your notes. There is a clear idea. And of course, norm of f at y is equal to norm of fy, which we have already proven to be norm of y. So fy is a bijection which is linear and which also preserves the norm. Therefore, it's an isometric isomorphism. That means L1 star is isometrically isomorphic to L infinity. which means essentially the L1 star is the same as an infinity as far as it being a normal linear space is concerned. So that finishes our theorem. Okay, now there are certain home assignments in your notes, right? Like to show that looking at the duals of Rn and Cn, with a certain norm, let me call it norm infinity, okay, norm 1, whatever. So you do those exercises, okay. There are certain home assignments that you would do, and it is important that you do that. Okay, now the next is this. Next we are going to do the same idea. We are going to show that LP star is equal to LQ, where 1 is less than P is less than infinity, and 1 by P plus 1 by Q is equal to 1. So LP star, that means p to power summable sequences, yani sequences of the type x1 xi I runs from 1 to infinity, such that summation mod of xi raised power p I runs from 1 to infinity is less than infinity. We know that it's a Banach space, a normal linear space under the norm of x is equal to summation modulus of xi raised power p I runs from 1 to infinity whole raised power 1 by p. So this is the norm I have, right? Okay, I want to show that it is equal to LQ with the restriction that 1 by P plus 1 by Q is equal to 1. It would tell me that if I take PE equal to 2, then Q must also be equal to 2, because 1 by 2 plus 1 by 2 is equal to 1. So it means L2 star is the same thing as L2. And how about L1? Now L1 we have already done. L infinity, suppose L3. What would be L3 star? As per this formula, the square summable sequences is the same as square summable sequences. It's isometrically isomorphic to that. And if I take 3, so it would be 1 by Q would be equal to 2 by 3. That means Q would be equal to 3 by 2. So L3 ka star would be L3 by 2 ka star. L3 by 2. And a L3 dual would be isometrically isomorphic to this. Now this has got nothing to, what is this space? This is all sequences of the type summation xk raised to power 3 by 2 is less than infinity, k runs from 1 to infinity. No issue, you just apply the p to power summable sequences, q to power summable sequences. The idea is same, the norm is defined in the same way. Okay, now let's start the proof of this. Now proof would be almost identical. Now again we talk about LP, and this Schauder basis EK, k runs from 1 to infinity, that you already know, right? So then I can write every x belonging to LP as x is equal to summation xk ek, k runs from 1 to infinity, right? So if f belongs to LP star, then I can apply it to vectors in LP. So it would be f of, what do I have? F of summation k runs from 1 to infinity. Sorry. F of x, I am in a hurry because, okay, this is equal to the same method, nothing different what I did in the previous theorem. If you see, it's almost identical except for the norm. Okay, so you go through the same process. If you look at your notes, it should be very clear. Following the same method, we get this proof, right? There is only a slight, what you call, you might have to use, but you've done that. The, what do you call, Cauchy-Schwarz inequality? No, Holder's inequality. You might have to use Holder inequality at some place. So that's the only difference. Otherwise, it is perfectly all right. You just look at your notes, you can do it. I don't think there should be any problem. If there is any problem, I am here. You just can contact me on WhatsApp, on telephone, and I will clear any doubts regarding this, right? Okay, that was P dual. So these were certain concrete duals that you would do, and I would move to another another idea what is called a complemented subspace of a normal linear space. Complemented subspace. So now if X is a normal linear space and Y is a subspace of X, and if there exists a map, what we call a projection, map P from X onto Y. This has to be a surjective map from X onto its subspace such that P is linear onto the hay from the start, and P square is equal to P. By that I mean P of X is equal to P of X. We call this condition idempotent. So it's a linear continuous idempotent map. If such a map exists, we say that Y is complemented in X. Okay. Now I can give an example. Now if we take R3 and I take its subspace. Okay, let me take R2, but I identify R2 by this thing x1 x2 0, such that x1 x2 belongs to a set of real numbers. In this way, R2 can be identified as a subspace. R2, if I define it like this, R2 is a subspace of X. So if I define a map P from R3 to R2, okay, by P of X. Now X in R3 would be P of X1, X2, X3 is equal to X1, X2, 0. Of course, this belongs to R2 by our identification of R2 with a subspace of R3. It's a proper subspace. Then P has all those properties. And it is given in your notes that it has all those properties. So indeed R3 is a complement, R2 is complemented in R3, which essentially means you can always write it as R2. So we can break it like this. I can write R3 as R2 direct sum R. That's the ultimate sort of result of such a condition, that if a subspace is complemented in, but not all subspaces are complemented in their vector spaces. For example, C0 is a subspace, means all sequences that converge to 0. Of course, it forms a subspace of L infinity. We have discussed this in the class. C0 is a subspace of L infinity, but C0 is never complemented in L infinity. In fact, this is an important result that you would do in your second course on functional analysis, I guess. So let me stop it here.